Let's now go through the normalization and boundary conditions for the infinite well. So in a prior video, I solved the differential equation, that was our energy eigenvalue equation, and found the condition for what C is. So I've written it this way, but C, these terms are coming from specifically the energy eigenvalue equation. Now the key is to remember that this is in fact only for x equals 0 to x equals L. Else, we said that these eigenfunctions actually have to equal 0 since our potential is infinite there. So this is going to be a piecewise function, but we've gotten to say this and now we can really just focus on this. So originally the differential equation gave us sines and cosines, but then I made the argument that since this is always 0 at x equals 0, remember that cosine of 0 is equal to 1. So the only way that we can always have this be 0 right at the edge is if we only have the sine terms. And the argument is that our wave function has to be continuous. So since it is in fact 0 out here, if our wave function is 0 here, then it has to be 0 right on the inside of that wall. So notice that the first derivative isn't continuous here. That's okay. When you have an infinite potential, your first derivative doesn't have to be continuous, but the function itself has to. So it has to go to 0 right at this infinitely rigid wall. So now let's try to figure out a little bit more about these coefficients. In particular, there's two coefficients we want a constraint on. We want a constraint on A, and we want a constraint on these E. And again, hopefully you have some sense for this infinite well. Only certain energies are allowed. This is something that, again, we've studied in prior classes. And the reason is these boundary conditions. So one idea is that these E sub I are being constrained by the boundaries. And then we have this coefficient A, which is going to be constrained by the normalization. So what do I mean by normalization? So we've said that when we have our position representation, we need to have a probability equal to 1 of finding our wave function. And when we do the probability, we would do psi star psi dx and integrate from negative infinity to infinity. That needs to equal 1. Now here's the key. We now actually have three different regions here, right? One region is from negative infinity to 0. We have some wave function there. And sorry, I've written it psi, but we're going to be working with these energy eigenfunctions. So okay, I have my energy eigenfunction, and I'll just shorten it. So star energy eigenfunction dx. Then I have my region from 0 to L. Again, my energy eigenfunction, which I'm trying to learn about, dx. And then my third one is from L to infinity. Again, my energy eigenfunction, dx. We know that this has to be 0 if we're not between 0 and L. So this term here is 0, this term here is 0. So it's important to note that when we're doing the normalization, we are really always starting from this term, but then because it's a piecewise function, we break it into three pieces, and two of those integrals are just clearly 0 because we're integrating 0 as our wave function. So what we're left with is that 1 needs to equal this integral. So I'm just going to set it up here. So 0 to L, the region where my wave function is non-zero. And now first, I need to take the complex conjugate of my function. So that's going to be A star, and then sine of this stuff on the inside. And for right now, I'm actually just going to keep leaving it as square root of Cx, because that's not necessarily going to matter. And then I have A sine of, again, the same thing, dx. So what's happening here? The goal is to use this to actually find A. Now, maybe there's a chance that A actually relates to this E on the inside. That's not actually going to be what happens. So that's the good news. So potentially you need to do your boundary conditions before your normalization. So when we're left with this, we actually can, in fact, pull out that A, right? A star A is just magnitude of A squared. So as we've seen in the past, there's some overall phase that you can choose. We'll choose A to be real and positive. And then we're left with the integral from 0 to L of sine squared some coefficient x dx. Now, what in fact is the integral of sine squared over a region? We in fact do need to know the boundary conditions of this, and one of the things you might notice here is that we're always back to 0. So there is some argument to be made here that we'll get that constraint on A. It is helpful to actually know what our boundary condition is first, to simplify this. And if you say, well, I have no idea what my integral of sine squared is, well, good news. There's this table of integrals in the back of the book, and if you look, there's going to be some sine squared. So for instance, integral indefinite of sine squared ax is equal to 1/2 x minus 1 over 2a sine ax cos ax. So you could even use that right now without necessarily knowing what this variable is, and from that maybe make an argument about what your integral is. So this sort of integral where you have a sinusoidal function squared, you're going to see that a lot. So having a table of integrals that you can look to is going to be really important. Getting used to doing some changes of variables, you need to do that. So if it's been a while since you've done some of these integration techniques, or if you maybe weren't that good to begin with, make sure that you're doing lots of practice, you're practicing these steps, and you're not just using your calculator or Wolfram Alpha to do it. You really need to be able to do these things by hand because we're going to be introducing so many different variables. A lot of times your calculator won't know what to do with it. So hopefully that this has been helpful for understanding the normalization. Again, that would be the final step here. Don't have room to do it. And then in the next video, I'll look at the boundary conditions.